and Our Life, SAOL, series of lectures, and they were started online during the pandemic. They have been open to all, to members, teachers, students, and the public at large. And the lectures have all
Women Scientists
aimed
Association
to augment our
registered
knowledge,
in Mumbai,
highlighting the science behind all subjects close to our life. These lectures have been well received by enthusiastic and interactive audiences. Now, many of these eminent scientists and doctors and technologists were the speakers for this series, and it has been shown as a rolling slide, the names of all the previous speakers. Let me extend, on behalf of IBSA, a very warm welcome for today's talk. The eminent speaker, scientist and astronomer Dr. Hashima Hassan from NASA, USA. Our lead discussants, Dr. Prajwal Shastri and Mr. Chintamani Pai, and all our members and our distinguished audience. Today's talk assumes double significance for us. Firstly, it is the 25th lecture, Silver Jubilee talk of the SAOL series, which was started, as I told you, during the pandemic times. Secondly, and even more important, is the topic of the talk today. Dr. Hassan covers today a very exhilarating subject, unlocking the secrets of the early universe using a very special telescope to peer into the sky, the James Webb Space Telescope, which was launched only in 2021 to orbit the Earth from the outer space. You would have all the entire audience, I'm sure, knows about the Hubble Space Telescope. It has been covered even in the high school books, which was launched in 1990 and which is still orbiting the Earth at about 350 miles or so in space. Dr. Hassan's telescope, the JWST, is much, much more powerful than the Hubble. She will tell you why it is so and how it is so. I am, like all of you, equally excited to learn all about this powerful instrument, its application, the instrumentation, and the involved high technology and its fallout.
We had that experience of being.
We are always curious to know if there is life beyond our Earth, anywhere in the outer space. We want to know if there is an answer. We want to know even a prediction. We would like to learn about the origin of this universe, confirm the existing theories, and also the origin of our own Earth. Now, Dr. Hassan may solve through her talk some of these enigmatic mysteries that shroud us. While we look forward to her talk, I would like to give a bird's eye view of our NGO IBSA for the benefit of those newcomers. IBSA is a non-profit, non-political NGO. We are 50 years old. Can you show the slides of the IBSA? We are 50 years old this year. The NGO was started by 12 eminent scientists who wanted to promote science in the society, bring about a rational and scientific attitude in the public, especially women, encourage women in science and girl students, inculcate scientific approach in people in all walks of life, and also set up community benefits for working women. Now you can see the slide which shows the entire IBSA building. This is located, our headquarters is located in Navi Mumbai, with 11 branches in the country and with more than 2,000 women members volunteers, we have come a long way in achieving our mandates. Now, I'm not going into the details of all our projects. They are all enlisted in our website, www.ivsa.net. This year is our Golden Jubilee year. We have set up a number of special science and technology programs for the celebration. We invite all of you to look for our events from the website and join in big numbers and support us in every way. Thank you. And over to our ex-president, Dr. Lalita Dhareshwar, to introduce our speakers.
Thank you very much, Devki. And I'm Dr. Lalita Dhareshwar, the immediate past president of Indian Women Scientists Association. And it's a great privilege and an honor to me to introduce Dr. Hashima Hassan to the audience. We have been waiting with a bated breath for the last several weeks for this particular talk, because this is the thing which has been in the news for the last 1 year, and we have been almost listening to this, what is happening in the space. And today, these secrets are going to be revealed by Dr. Hashima Hassan. She is the program scientist, NASA program scientist for New Star, the Keck Level Observatory, and ADCAR. She's the deputy program scientist for the James Webb Space Telescope, education and communication lead for astrophysics, executive secretary of the Astrophysics Advisory Committee, and she makes sure that each project's mission remains possible and true to NASA's strategic objectives. She has been the program scientist for many other NASA missions, such as the Wide Field Infrared Survey Explorer, Gravity and Extreme Magnetism SMEX GEMS, Stratospheric Observatory for Infrared Astronomy, Hubble Space Telescope, Explorer Program. From 2001 to 2006, she served as the lead for astronomy and physics research and analysis programs. She's a doctorate from the University from Oxford, UK, in theoretical nuclear physics. Till 1985, Dr. Hassan conducted postdoctoral research and held teaching positions in the areas of theoretical nuclear physics and in environmental science. She was the optical telescope assembly scientist at the Space Telescope Science Institute, Baltimore, till 1994, when she joined the NASA headquarters. She has received certification for the Senior Executive Service in 2004. Hassan has published articles in various peer-reviewed journals, such as the Astrophysical Journal, ICARUS, and publications of the Astronomical Society of the Pacific. She has been honored with prestigious awards and fellowships throughout her outstanding career, including the NASA Headquarters Exceptional Performance Award in 2008, the National Research Council Resident Research Associate from 1981 to 1983, Commonwealth Fellowship from 1973 to 1976, and received a gold medal for physics and merit award as a student. It is indeed a spectacular, your CV is spectacular, madam, and we are really thankful to the NASA website for having given us so much information about you, and we are really grateful to you for having accepted our invitation today to give this talk, and we are just waiting. I invite Dr. Hashima to start her talk. Thank you very much.
Good evening and namaskar. Thank you, Dr. Dhareshwar, for that kind introduction. It's indeed a great pleasure and honor for me to address the Indian Women Scientists Association. My career and my education was shaped by 6 institutions in India: Loreto Convent, Lucknow, Lucknow University, Aligarh Muslim University, Tata Institute of Fundamental Research in Mumbai, Pune University, and Bhabha Atomic Research Center. So a special hello to my fellow alumni from these institutions. I would also like to, at this time, recognize my childhood friend, Dr. Tanima Bose. We met in Loreto Convent, Lucknow in kindergarten, and our friendship has stood the test of time. And and it is really due to Tanima who introduced me to Dr. Dhareshwar. So thank you, Tanima. I'm now a US citizen, but as the poet Iqbal said, "Gurbat mein ho agar hum, rehta hai dil watan mein, samjho wahi hame bhi dil ho jahan hamara." Even if I am in a foreign land, my heart remains in the land of my birth. Consider me where my heart is. So today, my heart is with all of you. And it's with real pleasure that I bring you a glimpse of the James Webb Space Telescope. And as Dr. Dhareshwar has already said, it's the most powerful space telescope launched by humankind. So let me start by sharing my screen. I should just go to the top. So the James Webb Space Telescope is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. And we think of it as NASA's infrared light to the universe. Webb is a technological wonder. It will enable humankind to unlock the mysteries of the formation of the early universe. It's a tribute to the ingenuity and creativity of the human mind. With its 6.5-foot primary mirror and 4 powerful science instruments, it will study the first stars and galaxies, atmospheres of extrasolar planets, learn where elements that form life came from, and much more. Why do we launch telescopes in space? The reason is that the Earth's atmosphere filters out most of the wavelengths, and those that do go through are blurred. So NASA has launched many telescopes, but I showed 3 here. Hubble Space Telescope, which was launched in 1990, it's still operating, observes in the ultraviolet, visible, and near infrared. Chandra, named by the famous Indian astronomer, Dr. Chandrasekhar, which is also still operating, observes in the X-rays, and Spitzer observes in the infrared. So why do we need to observe in so many wavelengths? Because it expands the view of our universe. Each wavelength gives us a different view and gives us different science. Here are some examples. On the upper left-hand corner is a Chandra image, and the X-ray takes us right into the heart of the Crab Nebula, which was left behind by a supernova explosion. And you can see that the motion of the particles around the central pulsar are very clearly seen in the ring in this image taken over 20 years. On the upper right-hand corner is an image of the star Zeta Ophiuchi taken by Spitzer in infrared. The infrared light goes right through sees right through the dust, and we learn about the strong winds that being blown out by the star and giving the bow shock in the dust. The lower left-hand corner is a Hubble image of the Ring Nebula, showing us details of the ring. And on the lower right-hand side is a multi-wavelength image of Chandra, Hubble, and Spitzer of two interacting galaxies. And in this image, you're able to see the entire life history of massive stars, right from birth to their afterlife, sending out X-rays. But those were some examples closer to Earth. But what do we see is going further out in Earth? Here is an image taken by the Hubble Space Telescope, known as the Ultra Hubble Deep Field. It's an image of about 10,000 galaxies, showing galaxies going back to about 400 million years after the birth of the universe till today. And the light arriving at Earth from the furthest objects in the universe left those objects billions of years ago. So we are really looking back in time. We see those objects not as they are today, but as they appeared a long time ago. The universe started when a singularity which contained the entire mass and energy of the universe suddenly started expanding. This phenomenon, the scientists have named Big Bang, not because there was a big loud sound, but it was because of the sudden release of the mass and energy. Now, as the universe expands, the light in the universe stretches to longer wavelengths, and this is known as the cosmological redshift. The light, which started off as blue or ultraviolet when the stars and galaxies were born 13.5 billion years ago, by the time it reaches us, it has reached in the infrared. And it is this infrared light that Webb will observe. Here are some examples of what Webb can see. These are images on the left, are visible image taken by Hubble of the Eagle Nebula. And you can see that there are these dust clouds which are hiding stars which are being formed in there. The middle image is an infrared image by Hubble of the same region, and the infrared light from the stars goes right through the dust, and you can start seeing the star formation. And the image on the right is a mid-infrared image taken by Spitzer, which shows the dust clouds which are beginning to disintegrate. So here is just to remind you that the visible part of the spectrum is really very small. And that's where what Hubble sees, plus it sees ultraviolet and some of the infrared. But the James Webb Telescope will see a lot more and go almost into from the near to the mid-infrared. And Spitzer went a little further than that. So just to give you a little bit, remind you of the history of the cosmological history of the universe. As I stated, that it started with the Big Bang, and as the universe started expanding, it started cooling, and cosmic fluctuations took place. And after a while, elementary particles started forming, and there was a big soup of neutrons and protons and electrons. And the ordinary particles were coupled to the protons, the photons, and the photons were being scattered by the electrons, could not leave. But after a while, the neutrons and protons and electrons started combining And that period is known as recombination, and that decoupled ordinary matter from light. And for the first time, the photons left, and they form what is known as the cosmic microwave background. After that, there was still a big soup of of these elementary particles which were combining together to form neutral hydrogen and neutral helium. And while that process was taking place, it's known as the Dark Ages, because there was no star formation and no light leaving. So the neutral hydrogen atom clumps then started forming into clumps, and gravity then started putting these clumps together. And the first stars and galaxies were born roughly about 200 million years after the Big Bang. And that's when, and the period between recombination and the birth of the first stars and galaxies is known as the Dark Ages. And so what Webb will see will tell us what the star formation looked like, and it'll go back as far back as seeing the first stars and galaxies. And of course, it will also see the universe as it is today. So it'll go from today far back to about 200 million years since the birth of the universe. So the Webb's infrared observations will help create the first detailed snapshot of galaxies in the early universe and provide more information than before. The new data will allow analysis. The new data will allow. Sorry? Sorry, did you say something? The new data will allow analysis of individual objects to understand how the surrounding gas changed from neutral to ionized, creating the transparent universe we see today. Webb will also discover some of the first galaxies. Here again is a Hubble image, and the inset shows one of the earliest galaxies observable in this image. And as you can see, this galaxy is not very well formed. So it seems as though the early galaxies were not well formed, and evolution took place. And here is what we can call a flip book of galaxies. These are, again, images from the Hubble Ultra Deep Field, and showing galaxies going back in time. So you can see that the image way back, the little red dot is the furthest back galaxies, which is visible in this image. And as you get closer and closer to today, the galaxies are a little more formed till you see this nice spiral galaxy today, which, I mean, our Milky Way is also a spiral galaxy. So Webb will examine these early galaxies and the eras and follow it in new detail. And this will provide essential insight and help us learn more about how galaxies evolve. The galaxies change over time, as you can see from this image. They grow, they collide, and they merge with each other. And Webb will give us details of how all these processes take place. Here is a simulation of the JWST's multi-object spectrograph, which will have a huge impact on galaxy evolution. In this image below, you see that this spectrograph is capable of taking over 100 spectra of galaxies in one shot. And that's because there's a novel, what is called, the kind of little windows it's called a micro shutter array. And each of the shutters can be opened and closed depending on what observations the scientists want to make. And this colored image in the bottom shows that it is simulation of what you can see in the micro shutter array. Webb will also be able to dissect black holes and be able to understand more about about the nature of black holes. It'll give us the history, mergers, and growth of black holes and of star formation. In nearby galaxies, Webb will take high-resolution spectra to learn about the temperatures, speeds, and compositions of material at their centers. This data will be used to measure the mass of black holes at the center of galaxies by mapping speeds of the central gas and stars. Webb will study the feedback loop between central black holes, their powerful jets, and the formation of new stars in those galaxies. Webb could address broader questions of how galaxies form, including which came first, the galaxy or the black hole. Webb will also re-examine how stars form, live, and die. And here, again, just as a demonstration, are two images taken by Hubble in visible light. You can see that the dust hides the star formation, whereas on the right, in the image taken in infrared, it shows the infrared goes right through the dust, and you can start seeing the star formation. And Webb will be able to see this in much more detail and tell us the life history of stars. Its images and data will also help us learn about the physical and chemical properties of the stellar and planetary system, and it will give us insight into their formation. It will also detect molecules in star-forming regions, such as the one in the small Magellanic Cloud seen over here. Webb will capture spectacular infrared images in space, but its real power is spectroscopy. That's where you get the real science from, because spectroscopy, as this group certainly knows, is a scientific method for studying objects and materials based on detailed patterns of colors or wavelengths. So I don't think I need to explain to this group what spectroscopy means. So the astronomers will use spectra captured by Webb to study the mature stars of different size, mass, age, color, temperature, evolutionary stage, and formation environment. It will also help study newly forming stars cocooned in dense dark clouds of gas and dust, as I showed some examples earlier, cold molecular cloud that collapses to form stars, gas and dust ejected from dying stars, and molecules between stars. And closer to home, Webb will also help us re-examine our own solar system's planets. And it will observe the solar system from Mars and beyond. And here are some images taken by other satellites of Europa, which is Jupiter's moon. And I think this is a Hubble picture. And this has an ocean of ice sheets, water, warm water geysers, and we are going back with Webb to look at it. On the right, Titan, which is the Saturn moon, has clouds, hydrocarbon, rain, lakes, rivers, craters, dunes, weather, ice, rocks. So we already know something about it, but we'll go back with Webb and learn much more. The infrared light of Webb will also help us find distant planets. Now, planets are warm, And so they emit in infrared light, whereas their parent stars are bright and they are not so bright in infrared. So infrared is an ideal light for detecting planets around other stars. And so Webb will be able to detect smaller planets than those which have been detected by telescopes today. So this will be a great machine to find extrasolar planets. It will also be used to decode the planet's atmospheres. Here, as an example, is an atmosphere of the only planet we know, our planet Earth. And you can see that by taking the spectra, you can learn about the various elements and chemicals which are present on this planet. On our planet Earth, you can see there's carbon dioxide, water, oxygen, methane, and so on. Of course, we don't expect to see excuse me, an atmosphere like this around other planets, but we will see whatever there is. It will observe the chemistry of exoplanets. It will observe transits of exoplanets at different wavelengths of light. And, we hope to see able to measure water, carbon dioxide, methane, and other molecules. So how do we study the atmospheres of exoplanets with Webb? It will use a technique called transmission spectroscopy. It will observe the star's spectrum and then the exoplanet as it passes in front of the star. It will measure the spectrum as the exoplanet passes in front of it. And then the scientists will subtract the star spectrum with the spectrum to see which molecule the planet's atmosphere absorbed, which appears as a dip in the spectrum. Webb's data will also be transformed into models or maps of exoplanets to provide more information about exoplanets at each stage of their orbit. By using both imaging and spectroscopy, Webb will return incredible detail about planets we haven't been able to detect with other telescopes. Spectroscopy helps researchers identify the colors, temperatures, motion, and masses of celestial objects, helping us learn a lot more about these distant worlds. Now let's see some of the technology that went behind this remarkable telescope. So as I've mentioned, that it's a partnership between NASA, ESA, and CSA. It's led by Goddard Space Flight Center, which is a NASA center in Maryland. Its prime contractor is Northrop Grumman Space System in California. And the 4 science instruments are the near-infrared camera, which is the principal investigators is Marsha Ricci, Dr. Marsha Ricci at University of Arizona. The near-infrared spectrograph is principal investigator is at University of Edinburgh, and it's contribution of the European Space Agency. The mid-infrared instrument is a partnership between NASA and the European Space Agency, ESA, and the Jet Propulsion Lab leads the NASA partnership for the mid-infrared instrument. And the 5 guidance sensor and the near-infrared slitless spectrograph has been provided by the Canadian Space Agency. So in a quick summary of what Webb looks like, it has 18 hexagonal mirrors combined to make the primary mirror, which is 6.5 meters in diameter. There's a secondary mirror and there's a tertiary mirror. And all these are deployable. And they have to be kept at very cold at cryogenic temperatures. And the instruments, both the telescope and the instrument for far infrared performance. And this was launched on Ariane 5 rocket, which was provided by the European Space Agency. It's designed for a 5-year science mission, but we now expect to go much beyond 10 years. And the science themes, as I mentioned earlier, are the end of dark ages, first light, assembly of galaxies, birth of stars, and planetary systems. Okay, Webb is really a feat of engineering. In this image, you see on the left is the big primary mirror. It's inside the clean room at Goddard Space Flight Center. On the upper right-hand corner, you see 2 of the wings of the mirror are folded back. And on the lower image is the mirror with the sun shield under it at Northrop Grumman facility in California. Now, just to tell you a little bit about the Webb mirror, just to show the power of Webb compared to Hubble, here's the size of the mirror, 6.5 meters, compared to 2.4 meters of Hubble. And the power of any telescope, as you know, is the size of, it comes from the size of the mirror, because you can think of the mirror as a light bucket. The more light it will collect, the fainter and more distant objects it can see. So that's what gives Webb its greatest power, that it can see fainter and much more distant objects because it can collect much more light. So the 18 primary mirror segments are made of beryllium, which is a very tough but light material. And for going into space, it's important to get a light material. The primary mirror is elliptical, a secondary is hyperbolic, and the tertiary mirror is a flat steering mirror at the back. The reason that there are 3 mirrors is to remove the various aberrations. The secondary mirror removes the the spherical aberration, and the tertiary mirror removes the astigmatism. And since it's a wide field of view, you need to remove all these errors so that you get nice, sharp images. And the steering mirror is there to remove the vibrations in the telescope and give a nice, stable image. So this mirror is diffraction limited at 2 microns. It's the operation temperature is 40 degrees Kelvin, and it has been polished to be of the correct shape when it is cold at that temperature. So yeah, also there are 6 degrees of freedom of to adjust the radius of curvature, and I'll say a little bit more about that in the next page. So here is a telescope overview. On the left-hand side is a ray diagram showing the light hitting the primary mirror, then it hits the secondary, comes to a Cassegrain focus, and then goes to the tertiary mirror to remove the remaining aberrations, then goes to a fine steering mirror before going to the focal surface and the science instruments. The image on the top right-hand corner is that of the actuators, which are placed behind each segment. And so there's one actuator at each corner of the hexagonal segment and one at the center. By adjusting these 7 actuators, it gives you 7 degrees of freedom to adjust the shape of the mirror. And that is really important because as you can see, with 18 segments, to get them to work together as one mirror, you really need to adjust each segment very finely. they can all work together in unison. At the bottom is an image showing the telescope about to enter a test chamber, which was specially designed at Johnson Space Center in Texas, in Houston, Texas. This chamber was originally used for testing the Apollo mission, and it was reconfigured to check Webb. The lesson we learned from Hubble was that the optics of the telescope should be checked before it is launched. While Hubble was in low Earth orbit and we could send a servicing mission, James Webb will be too far away for a servicing mission. So a lot of tests were done, and that was one reason why it took so long. Now we know that it is in orbit, and here is what is called a selfie, and I think we all must have seen it. This is the actual mirror in space, taken by an image taken by a camera on the telescope. This image I showed you before. This is the optical telescope element, which is the telescope and the science instruments, and the big sun shield, which protects it from the heat of the sun. So let me say a little bit about the sun shield. This is made of 5 layers of a very light and strong material called kapton, which is capable of reflecting the heat of the sun. And the bottom 2 layers are coated with special material, which can reflect the heat of the sun better. And so these 5 layers keep the telescope cold from the heat of the sun and the earth, and so that it is at its operating temperature. So I've mentioned the 5 science instruments, each designed to do achieve different science goals. And the near spec will be used to study many distant faint galaxies. The nearest is study the composition of exoplanets' atmospheres, observe distant galaxies, examine bright objects that are very close together. The near cam will study the earliest stars and galaxies in the process of formation, stars in nearby galaxies, young stars in the Milky Way, and objects from a distant region of our solar system called the Kuiper Belt. It also can track the motion of exoplanets as they orbit their star. The mid-infrared instrument looks at cooler objects like debris disks around stars, which emit most of the light in the mid-infrared, and extremely distant galaxies whose light has shifted into the mid-infrared over time. So for those who are more interested in the details, this is a slide you can look at later, but I won't go into details over this. So now, where is Webb's orbit? Webb is situated at 1.5 million kilometers from the Earth at a point called L2, which is a semi-stable point where the gravity of the Earth and the Moon and the Sun is balanced. And Webb orbits this with the sun shield so that the sun shield is pointed towards the sun and keeps the telescope cold. And keeps the telescope cold. Yes, sorry, there was a phone call. I had to stop it. But since L2 is a semi-stable point, Webb has to be given a few thrusts to keep it in its orbit. So here is an image showing you on the left-hand side the sun shield. On the right-hand side, you see the sun-facing side of the sun shield, which has the star trackers and the steering and control model. And this is the Webb's unfolding sequence. And at the end, I will have a video of it. So here's the video. Just let me try and get to it. Yeah. Here's the video. So the first thing that came out was the solar panel, Stargate, and the antenna, and then the sun shield started unfolding. First one side came out, then the other side came out, and then they separated and tensioned. All this was a very complex procedure, but it went beautifully, and everything is working well. And then the mirror started unfolding. No, first it came, the shaft came out, so the mirror was free. Yeah, see, the shaft comes out, and then it started the secondary mirror, and then the ends started unfolding. And so the and all this was a very complex procedure, but it went extremely well. So how do we talk to Hubble? So the high gain antenna in Hubble, to Webb. So the high gain antenna Webb communicates with the Deep Space Network in Goldstone, California, which then sends its data to Space Telescope Science Institute in Baltimore, which has the operation center for the Hubble. So, for the Webb. Sorry, I keep saying Hubble. So it is the operation center for Webb. And the commands from Space Telescope Science Institute then go to the Deep Space Network and then onto the high gain antenna on Webb. So that is the communication process with Webb. So where are we in Webb operation? Here are some of the main points. It was launched on Christmas Day of 21. The sun shield was deployed, then the mirror deployments took place, and then it arrived at L2. And this is what we call the 29 days at edge. It was a very, very tense moment because there were so many things could have gone wrong, but everything went well. Then the telescope went through a cooling. The mirrors were aligned. They're all aligned now. Right now, we are at the instrument calibration stage. And once the instruments are calibrated, the commissioning will be complete and we will be ready to take science. Now, Webb is an international collaboration. It involved 14 countries and 27 states across the United States, and it cost the United States taxpayer $10 billion in addition to the contributions from ESA and CSA. So here's a quick journey of Webb from the time it was assembled at Goddard Space Flight Center. From there, it went, it was placed in a special container called the STARS container, which was made for the Space Telescope. It was placed in a Department of Defense plane, which was also specially, the hold of it was specially designed to put the telescope inside, reconfigured, and then it flew to Texas, to Johnson Space Center for the optical tests, and then it flew to California, Northrop Grumman, where it was integrated into the spacecraft, the sun shield and the spacecraft, and then it went by ship, MN Colibri, through the Suez Canal to the launch site in Kourou, French Guiana, South America, because that's where the spaceport for ESA is, and it's also the right place for launching Webb to get it into its orbit at L2. So it had a beautiful launch on Christmas Day, and it is now at L2. So just for fun, here are some pictures of Webb being loaded into its special container, Space Telescope Transport for Air, Road, and Sea, the STARS container, which I showed you earlier. And here it's starting its journey from Northrop Grumman Space Park facility in Redondo Beach, California. And there's a video of it on the website for Webb where they actually show it going through the streets of Los Angeles at night. It's quite spectacular. Here it's approaching its launch site in the ship MN Colibri that carried it through the Panama Canal. And here it's approaching Kourou, French Guiana for the European spaceport. And then December 2021, we had a perfect launch where Ariane 5 took Webb into its orbit on its way to its final destination. And again, the NASA website has the video of the launch. And if you see it, there's actually a picture on the launch vehicle which shows Webb leaving the telescope and the solar panel and the high gain antenna being deployed in real time. So here's a still picture of that, which was taken by the rocket as it left the rocket. But if you see the video, you'll actually see it leaving the rocket. Here are some pictures of which have been released as Webb was being put into focus. So the left side shows the images of a star in each of the mirror segments. And so as you can see, at first the mirrors are not aligned. So the images are kind of scattered around, and then the alignment process starts. And then the second image, you see each mirror has been perfectly aligned to have the image at the center of the mirror. And on the third image, you see each of the mirrors is then turned so that the image is stacked into one single perfect image. Now, this is the image you see here is a coarse image, but further alignment took place after that, and the telescope is now perfectly focused, and it's here is the full alignment image, and the spikes in it are an artifact of the 18 mirror segments, but they do not interfere with doing science. And although this is just an image of the focus,
James Webb type telescope. वहाँ के कोई scientist Indian वो दे
Sorry? What did you say? Okay.
No, there was some interruption. Yeah, sorry.
Okay. So this is an image of the perfectly aligned telescope. And here you can see this image is actually here to show the perfect alignment of the telescope, but you can already see those beautiful galaxies in the background, although the instruments isn't quite ready for science, but it gives you a taste of what is ahead for us. So, we are already beginning to see these beautiful images of galaxies. And so just to give you an idea of what the scientific discovery potential of Webb could be, here's a comparison. On the left-hand side, you see Hubble, and there were 4 scientific objectives of Hubble to study the distance scale, origin and evolution of solar system, intensities of supernovae, and gas and galaxies and quasar absorption line. And we have 4 science goals for Webb, which I've mentioned before. But look what happened once Hubble went into operation. In addition to the 4 science goals in white, all those discoveries in red are something that we never imagined. We didn't even know about when Hubble went. And Hubble made these remarkable discoveries, including the dark energy, which led to a Nobel Prize. So what will be the new discoveries of Webb? That, I think, for me, is the most exciting thing about Webb, that we will certainly learn about the 4 science goals, which themselves are very audacious. But what else will we learn? And for those in the audience who are interested in actually analyzing Webb data and doing science with it, I'd like to tell you that everyone has an opportunity to send in proposals to observe with Webb. But even if you don't send a proposal, or you are too young right now to send a proposal, but would like to do so later on, but would like to analyze the data later on, all the data that will be obtained from Webb is going to be put in a public archive, the Mikulski Archive for Space Telescopes, which already contains data from Hubble and TESS and all the other instruments which operate in the ultraviolet and visible. But MAST will also contain Webb data, and anyone can go to MAST and download the data and analyze it. So it's really is a machine for everyone. So I hope some of the students and scientists in this audience will be excited enough to analyze Webb data one day. And finally, I'd like to make you aware of this really nice interactive website, which you can go to, and if you click on each of these little icons here, which says Webbitorium, Library, Planetarium, etc., it'll lead you into some very exciting material about Webb. So I would encourage you to investigate more about Webb by going to this portal. Plus, there are lots of other websites out there. So thank you. I hope I've been able to whet your appetite for the wonderful science of Webb. And we are all excitedly looking forward to the first images probably in maybe in a month or so. And so thank you.
Oh, thank you, Dr. Hashima. It is something, I mean, you have taken us far into the space, really. I mean, unimaginable complexity of the whole thing, really unimaginable. And it's something which is too good to be true, I would say, you know. And now, you know, to carry on the discussions further and to make way for the discussions for the people who are not in the area of astronomy, astrophysics, and space, we have structured this entire program in a way that Dr. Hashima's talk will be followed by discussions initiated by 2 main discussants, that is Dr. Prajwal Shastri and Mr. Chintamani. The reason for doing these 2 people, they are in the 2 sides of the, you know, one is a very senior scientist, Professor Prajwal Shastri, and as you will see, Mr. Chintamani is a just upcoming astronomer and an entrepreneur. Let me introduce you all to Professor Prajwal Shastri. She has been an astrophysicist for nearly 4 decades, and her core research interest is the empirical investigation of giant black holes that are found in the center of distant galaxies. She strongly feels that nurturing learning environments pave the way towards excellence. And she's an MSc from Institute IIT Bombay, PhD from TIFR Bombay. And her PhD affiliations, post-PhD affiliations are numerous. Starting at present, she is with the International Center for Radio Astronomy and Research. And prior to that, International Center for Theoretical Sciences, TIFR Senior Associate, and so on and so forth. So many. She has more than 50 research publications in refereed journals. and has held leadership roles in many of organizational activities and also held honorary community service positions. Dr. Prajwal Shastri, and now I would like to introduce you to Mr. Chintamani. Can we go to the next slide, please? Yeah, next slide. I think the reason why we have initiated this discussions, first from a very senior scientist, then from a very young scientist, is so that it bridges the two generations, together. And it is really something very interesting, the way the two will look at the things, So Chintamani is a founding member of Space Geeks, which is a young startup working in the domain of space and allied areas. And it's a group of young researchers who have come together to work in field of space, the ongoing fourth industrial revolution. And it aims to generate a passion for space, aspires to connect everyone to space by contributing in Space Foundation technology to generate opportunities. He's a scholar, PhD scholar from University of Mumbai, and he has 10 research papers, including international peer-reviewed journals. He has presented his research in many international conferences and workshops, and last year he was selected for the NASA Insight Seers program from NASA Insight mission team to experience the work of interplanetary space mission. And recently, his award includes the Best Poster Award at the Department of Atomic Energy in 2018, and so on and so forth. So I request Dr. Prajwal Shastri to initiate this discussion, and so that you make a way and for the audience, because this James Webb Space Telescope is a very, very complex instrument. So we, all of us, it's 1 hour from you is too less for us to really grasp the meaning, understand, so that we could ask you intelligent questions. So that's the reason why we have called Dr. Prajwal Shastri and Chintamani here. So Dr. Prajwal Shastri, can you please start your discussion?
Thank you very much, Lalita. And thanks, Hashima, for that wonderful talk and giving us this exciting glimpse. And I'm so glad that you also highlighted the fact that NASA, in its typical fashion, makes data public. And not only that, NASA invests a lot in creating very user-friendly front ends so that the data can really be universally used and highlight this idea of the sky being a universal laboratory. So thanks very much for your lecture. So first I thought I would sort of try and get you to respond to the fact that we have pretty direct evidence for a supermassive black hole in the center of our Milky Way, for which infrared light was key. And subsequently, the Event Horizon Telescope has also been peering through the dust in the Milky Way to get a glimpse at the physics that's happening around this supermassive black hole. So how are Webb data expected to complement these studies, broadly speaking?
So Webb will really be looking at more detail. It can actually look at the same thing with more detail because of the infrared light. And plus, more importantly, it will look back in time. It'll be able to see if there were black holes were formed at the time of creation of the universe. We still don't know whether the black holes came first or the stars came first. That's still a controversy going on about that. And so with the Webb observations, we hope to be able to certainly learn more about it. Whether we'll be able to solve the controversy or not, we can't say right now, but we'll certainly learn a lot more about the black holes which came at the early, at the start of the universe. So the very first black holes that came. And there was, in fact, just yesterday I was reading about some observation where they think that they've seen an object which was about 200 million years after the Big Bang, which they think could be either a starburst galaxy or a black hole. And so they have actually, I forget the name of the scientists, they have actually got a proposal in with Webb to observe that.
Right. Yeah, I was actually asking about the specific supermassive black hole in the center of our Milky Way. The Event Horizon Telescope has been taking images and observed a whole bunch in 2017. I would have expected that Webb, with its imaging, will be able to complement those studies because much more will be visible to Webb with its diffraction limited resolution. Would you be able to comment on that? Yeah.
Well, you're the expert on black holes, but yes, I'm sure. I'm sure Webb will certainly give you a lot more details than the current telescopes do, because what you really see with the Event Horizon Telescope is the motion of the gas and stars or whatever, the material around the black hole. So you will learn more about that material, the velocity of the material, the mass of the material, and so and that's how you learn about the black hole. So you don't actually observe it directly, but the motions of the materials around it.
Right.
And with a resolution of Webb, you'll be able to get more details, learn more about the velocities. I think that will maybe the most important thing, and the masses.
Right. So you talked about the advantage that Webb has in planet discovery and its ability to find much smaller planets than we have been able to do before. So I was wondering as to what is the current state of the art in terms of what is the volume of the Milky Way where we have detected exoplanets, and how will Webb expand this zone? Because presumably it can look at fainter objects and therefore more distant objects.
So right now, I think the count is 5,000 of the number of exoplanets that have been observed by both Kepler and TESS put together. As I said, with its greater resolution, it will be able to detect more planets, not only smaller planets, but other planets also. It will be able to detect more of them further out as well as inside. How many it will detect, we can't tell. And I think that's where all those question marks come.
Right.
Yeah.
So you mentioned the very early galaxies that Webb is expected to see. So, you had that visualization of the life of the universe. I was wondering is it possible to show us which era will Webb provide a new window onto in terms of galaxy formation?
It'll start at about 200 million years after the Big Bang, when the first stars and galaxies started forming. And Hubble has gone back to like 400 million years. So we like to say like Hubble has seen toddler galaxies, but Webb will see baby galaxies.
Yeah, that's great. Yeah,
Okay.
that's nice.
So
should I?
Chintamani would like to ask something now, maybe?
Yes, first of all, thank you for such an exciting and highly informative talk. And I feel very fortunate to be part of this event with Dr. Hashima Hassan, who has been the lead program scientist with WST, and she's also heading the education and outreach, which is very important, I feel, as a part of the any space program, because you're having the taxpayers' money and you want to take the space mission to the masses. And thank you, ma'am, for giving such a fabulous talk. So I will slightly go to the slightly technical aspect of the telescope, since my interest lies slightly in the photonics and instrumentation. So my question to ma'am is, how do you, could you please enlighten us about these novel technologies which have been used in JWST, especially the heat shield. The heat shields, which are like multiple layers, which step by step cut down the heat flux, and then at the core of the telescope, which is like very novel technology. I was reading about it, which is called as thermoacoustic cooling. So if you could just throw some light on that for audience and students and space enthusiasts.
I think your question is, how do we keep the telescope cold with the sun shield?
Hold with the sun shield and the core aspect of the thermoacoustic cooling, which is the heart of the telescope.
Okay, so yeah, so the telescope is kept cold by what we call passive cooling. So it's like when you put an umbrella on your head and you cool yourself. So that's basically what you can think of the sun shield as, like a big umbrella. And so, as I mentioned, the material it is made of and the coating that it's done in the bottom shield is very reflective of the heat. And there are 5 layers so that, it gets cooler at each layer as it goes up. So it's totally passive cooling, nothing more complicated than that, other than, making sure that the sun shield has the right technology to do that. There is another cooling mechanism for one of the science instruments, the mid-infrared instrument. Since that operates at a slightly longer wavelength than the near-infrared, that instrument has to be kept very cold. And so there's a refrigerator there. It's like your home refrigerator. It uses liquid helium, which is cycled just like a refrigerator. So, but it's never been done in space. So that's why it was really new and important technology.
Thank you. So my next question is, since from the Apollo missions, we have seen that there have been always spin-offs from NASA missions. So do you see any spin-offs from missions like JWST?
Oh, if you mean technology spin-offs, yes, there have been many spin-offs. I'll just mention a couple. As I mentioned that this is the mirror is made of beryllium. And this material is light, hard, and very strong. And it is being used in airplanes and a lot of other things which need light and strong material. So that is one spin-off. Another one is the technology that was used for testing the mirror, the optics of the mirror. So the software that was developed is being used for eye surgery. And and also another thing beryllium is being used for is for gears and so on. So these are just a couple of spin-offs I'm mentioning, but there are really many more, and I think you'll find them on the NASA website.
Thank you. Then my maybe the last question is related to meteoroids or dust particles. There is always a possibility that they can strike the surface. So how that is being taken care of with JWST?
I didn't quite understand the question.
Since it is a space-based telescope, and you also always have dust particles, meteoroids, which are in space traveling at large speeds. So there is a possibility that they can strike the surface. So I mean, how that has been taken care of to protect the...
Yeah. So your question is whether if it gets hit by micrometeorites. Yeah. So we certainly, that's something we worried a lot about, and a lot of studies were done. And as you know, that there are some telescopes already there at L2. So we looked at them and looked at their studies, and it was determined that the probability of that happening is very, very low. If it does happen, I don't think there's anything we can do about it because it is at 1 million miles. but it was determined that the probability is so low that it's worth putting the telescope there. Yeah, we certainly worried a lot about that. That's a very important issue.
Yes. Now, could
Very
we
much.
have the questions from the audience, please? There are some questions to you, for you, Dr. Hashima. First one is, will the Webb telescope give any information about the dark matter and dark energy? This is the question, yes.
No, certainly that is one of the goals. I won't say one of the goals of the mission, but certainly one of the goals of the scientists.
Yes.
And there are some proposals from scientists to do studies which will give more information on dark matter and dark energy.
Yes.
For example, when you look back at the very first stars and galaxies, as I mentioned, the black hole, the question was if they do see a black hole, where did it come from? Was there a lot of dark matter over there which caused it? So yes, it will give information on that.
Yeah. How far back will Webb be able to see? This is the second question. How far back?
Go back to see like 200 million years from the birth of the universe. So that's like about 13.2 billion years, 13.3 billion years back in time.
Yes. And there is a comment from another person from the audience. Evolution of technical physics to engineering physics to deploy Webb science instruments is a chapter in the history of technology. This is what she's telling. I mean, one of the audience is making a comment. Yeah. The second, the other question is, when the time was zero, how the universe took birth from the single particle and from where this single particle was generated. I think it's a student.
Yes, I mean, I think no one knows the answer to that question, and I hope you as a student will be able to get it. That's something we really don't know, where this singularity came from and why it suddenly became unstable.
Yes. Then there is one more question. 200 million years would be the earliest images captured from time zero. Or could there be pleasant surprises wherein it could go even closer to time zero? This is what one of the audience person is asking you. It's possible.
Yeah, in some sense, we have gone a little bit closer with the cosmic microwave background, because that was the first photons that were released and have reached us as cosmic rays, which are even longer than infrared. But that was before the stars and the galaxies were formed. And so the cosmic microwave background explorer, who the PI was Dr. John Mather, who actually got a Nobel Prize for that investigation.
Yes.
But we haven't, I don't think we can, well, at least right now, nobody has proposed a way to, I don't say we can't, but no one has proposed a way to observe further back than that.
Yes. And Mr. Ajay Kumar has given a comment that L2 is a point of almost zero gravitational effect. So I guess hopefully there isn't any worry about meteorites. This is what he's put as his comment. So that's the reason why we don't have to fear the, striking of any meteorites on the JWST. This is the comment. Okay. Then there is another question. When is the next asteroid likely to hit Earth? I mean, it's quite a different question, but would you like to? Yeah.
Yes, so we have at NASA something called a Near Earth Object Program, where we track all the asteroids, and this was actually a congressionally mandated program, precisely for that reason, to see if any asteroid comes close enough to Earth to be able to strike it. And I think last year there was one which was coming close, but still not close enough to hit it. So we are tracking it. We can't predict when or if it will happen, but it's certainly thought to be important enough that we are tracking it. We have one of our satellites, WISE, which you mentioned I was program scientist for. After it stopped doing astrophysics, it was turned towards observing near-Earth objects, NEO-WISE. So that is one NASA mission which is observing it other than ground-based telescopes.
Dr. Suresh Kumar is asking a question. How does one go back in time? Please explain again if I have missed it. So
yes, as I mentioned in one of my slides, the light that is coming from distant objects takes time to reach us. So just to put it in perspective, the light from our own sun takes about 6 to 8 minutes to reach us.
yes.
So it left the sun 6 minutes ago. So that we if you look at the sun, you're looking at it as it was 6 minutes ago, not what it is now. So if you're looking at galaxies and stars where the light left billions of years ago, you are like looking back in time. You're looking at them the way they were at that time. So that's what looking back in time means.
Yeah. There are several very, very appreciative comments, Dr. Hashima, that your talk has been most exciting talk. And there have been so many, students here attending. And I'm sure it would have been very exciting and inspiring to them. And it will really set a track in their mind, ignite their minds, so to say. I hope that it does that. And I think, Dr. Prajwal, do you have anything to say further in this? Any questions would you like to ask her, or any comments or anything else?
There is a question from.
I was just wondering whether Hashima could, she showed some really cute images of the performance verification phase, where you showed how the focusing was done first of the individual elements and then all together. So I was wondering if any of these performance verification images had scientific potential.
They are not meant for doing science. I know people have asked that question.
But I was wondering, just by chance, whether...
well, I guess some creative scientists could always do something, but no, they are not science images.
Okay, really. So,
Ma'am,
yes.
We have a question from Mr. Srinivas Lakshman, who is a space journalist and space enthusiast. So his question is, when will JWST be formally commissioned, and can you highlight some of the future milestones?
I pointed all the milestones that we had. The last one is the release of the first images. Once all the instruments have been got ready for science. Right now, only the mid-infrared instrument is left. We are still working on that, commissioning the mid-infrared. All the others have been commissioned. So as soon as the mid-infrared instrument is commissioned, that's when we'll start taking science images. So probably in about a month or so, that's the last milestone.
Mm.
And after that, it will start taking data from the proposals that the scientists have proposed. And a list of all those proposals is on the website.
Dr. Hashima, I have a very simple question as to when did the actual work on this telescope start? How many years did it take for the scientists and engineers to actually make it work and set it into space? It would have taken quite a number of years, no?
It took a lot of years. now I don't know when you consider start of the work, but it in 95 was the first studies was started of the
Okay.
telescope.
Yes.
Yeah. And when we cut metal, I would think, gosh, probably around somewhere around 2000. I don't remember the exact date,
Yeah.
but I would say somewhere around 2000 is
Yes.
when we first
And
cut metal.
maybe how many hundreds of people are involved in this making of this telescope?
Oh,
or maybe
absolutely.
thousands?
I would say thousands are
Thousands.
involved.
Yeah.
Yeah.
I mean, it's a marvel, engineering marvel, and it's really, I mean, really,
Yeah.
I mean, it's unimaginable. Yeah.
And as I said, 14 countries, 27 states, you know, some were just making the nuts and bolts, which are so specialized. And,
yeah. Correct. Yeah, I know. It's
From
been a
same
wonderful.
context,
Yes.
in the same context, I would like to ask another question. So in all these years, right, from the inception of JWST till its launch, would you like to share any moments of up and down, and how how the whole team of so many scientists, engineers, how they were coordinating the event? I mean, I'm sure must have been a lot of challenges. So how can you share any incidences which will really inspire youngsters and students over here?
Wow. Yes, there were lots of ups and downs, but all I will say is keep your ups, you know, don't let the downs get you. There will always be downs, and you have to figure out how to solve the problem.
Yes.
And we had a lot of downs, not only, I would say, there were fewer with the technology than the actual cost and management and cost. And then since this is a government project, you have to get the way the US government works, you have to get the budget every year. So every year you have to convince Congress that this is something that we really need to do. And so they can give you the budget to do it. So they have hearings. We tell them what we are doing, and then the scientists go and say that, yeah, we still want it. So there have been stages where Congress says, okay, if you don't do it by such and such date, your budget will be cut. But let me tell you a couple of moments in my own life while as program scientist of this mission. One which was, for me, I think was one of the really hardest one was when we were deciding which instruments should be put onto Webb. So the NIRCam and the NIRSpec were straight, but the mid-infrared instrument was, the management was hesitant because it would add to cost. So I will say that my supervisor, who was at that time Dr. Ann Kinney, she had to go to her boss, Dr. Ed Weiler, and convince him that this instrument is very important for Webb. And then it was my job to then we had to negotiate with the Europeans which part they did and which part we did. So that was a part which I was really central in the negotiation. And then after that, once it was decided what part we did, we had to decide which NASA center will manage the mid-infrared instrument. So I had to organize that review also. And it was on September 11, on 9/11 that I was conducting that review. So that stands in my mind. So whenever Miri is mentioned, I think of that. But we overcame everything at the end. And again, another thing that I'll mention about Webb is that the testing was very hard, and that's why it took so much time. So every time the test, but we had to make sure that it worked because, as I said, there was no servicing mission. So testing is really important. Testing.
Thank you so much. And I think Dr. Suresh Kumar had raised his hand. Would you like to ask the question, Dr. Suresh Kumar? I just saw the hand raised.
Thank you.
Yeah.
Thank you. It's a very simple question. Maybe I'm not in the field. When we say we observe a object 1 billion light year away, so in fact, in separating time in the expansion, it must have taken much more than 1 billion year. So I'm a little confused. What is the actual distance then?
So no, I didn't understand the question. Can you repeat it for me?
No, any object in the space, we say that it is a light is coming after 1 billion year. Okay.
Right.
It is a 1 billion light year away. But in actual, since it is expanding not more than velocity of light, so actual time taken would have been much more than 1 billion year.
It, it's not expanding faster than the velocity of light. It's the light started 13.5 billion years ago. That's when the Big Bang took place, not 1 billion, 13.5 billion years ago.
Okay.
And so till now, the telescopes which have seen the objects, those objects were 400 million years after the birth of the universe. So their light is reaching us now. And what Webb will look at will be objects where the light, 200 million years after the birth of the universe, the light that left those objects and is reaching us now will be observed by Webb. It has reached in the infrared.
Maybe I will again clarify. I am maybe confused. I am saying, say any object which is 1 billion year away from us or from the telescope, 1 billion year away. When we say that,
Yeah.
But in actual case, that separation time would have taken more than 1 billion year because the expansion rate is less than the velocity of light. So I'm a little confused. What is the distance then, time-wise?
I'm not sure I perfectly understand your question, but when light leaves an object, it travels, and as the universe expands, the light stretches, and so when it reaches us, it has stretched from its original wavelength.
Yeah, must be something like this because simply 1 billion year taking light year may not be the correct distance, right?
Yeah.
Account for the change of frequency.
Thank you. I have to think about it.
So I think we have finished, completed all the questions. May I ask Dr. Devaki Ramanathan to propose the vote of thanks, please? Dr. Devaki Ramanathan, are you there? Okay, I'm not very sure. I don't know whether, anyway, since she's not, yeah. Dr. Devaki Ramanathan, are you there? Yeah.
I was muted. Okay.
Yeah.
Thank you, Lalita. I'm very happy to give the vote of thanks also, but it is a very difficult task for me because it has been a total marathon run for me. For billions of years, seeing the stars and all is not an easy job. It was very thrilling a very thrilling journey of the whole universe.